Welcome, everyone. Today we have Yuntian Deng. He's an assistant professor at University of Waterloo and is also a visiting professor at NVIDIA under the supervision of Professor Yejin Choi. His research interests include natural language processing and machine learning. Today we would be discussing implicit chain of thought. So I'll pass it on to Yuntian.
Yes, thank you for the introduction. So this is work I did with my advisors, Professor Yejin Choi, who's actually at Stanford and NVIDIA right now, and also my PhD co-advisor, Professor Schieber at Harvard University. So before we get into language model reasoning, I revisit how humans reason, because I presume people might be able to get some inspiration from the human reasoning system. So in his famous book, Thinking Fast and Slow, Kieman proposed the idea that there are two different types of reasoning systems in the human brain. There's the system one reasoning, which is happening really fast and intuitive, thinking without any effort. Examples of system one reasoning include computing simple math, like 2 + 2 = 4, or completing some common phrases, like bread and butter. So when we do these tasks, we do not need to use significant amount of mental efforts and can directly get the answer. But as opposed to system one reasoning, there's also the system two reasoning, which is slower, requires efforts, and requires deliberate thinking. So examples of these include computing some just a little bit more complex math problems, such as what's the product of 23 and 47. You cannot most people cannot directly give an answer by just looking at this expression, right? And some other examples include like solving a puzzle, like Wordle, or some logic word puzzles. So in the human brain, there's the boundary between system one reasoning and system two reasoning is actually not always clear. So actually, there's this process of internalizing, or in some literature called compiling, system two reasoning into system one reasoning. For example, let's imagine when someone begins learning a music instrument like piano, they start by trying to memorize the mapping from a music note into a key on the keyboard. And this is a pretty effortful process. And initially, you might need to really think about which key you should press based on which music note. But eventually, this process becomes automated through repeated practice, such that eventually you don't need to actually think about how to move your fingers when you look at individual notes. Instead, you focus on something that's more high level, like the flow of the music. So this internalization process reduces the mental load of solving a task, and also it obviously makes execution way faster. For example, if a great pianist needs to deliberately think about which key they would press based on which kind of music note, obviously that's probably too slow when they were performing in front of the audience. And also, what's more, by internalizing system two reasoning into system one reasoning, it enables completing more or focusing the attention on more complex tasks. For example, let's say when we were a little baby, we might need to learn how to move normal muscles on our legs to walk around. But eventually, when we become adults, we don't spend a lot of mental efforts trying to think how to move our muscles to walk around. We can just focus on other things in our cognitive mind. So we have been mostly talking about human reasoning process until this point, but obviously the focus of my talk is on language models. So what's the analog between reasoning in language models versus reasoning in humans? So to draw a parallel, let's first look at system two reasoning. So how does language models perform system two reasoning, or can they actually perform system two reasoning? Let's look at this example. So this is an example problem of a Greek school math problem. It's actually pretty simple. I can read the problem because it's kind of only a Greek school math problem, and we can probably solve it on the fly. So the problem says, assume its bookshelf has 120 books. She has 10 books on history, twice that many books on literature, which means she has 20 books on literature, and the rest are science books. How many science books does assuming have? So there's 10 books on history. So if a person wants to solve it, it's like 10 books on history, 20 books on literature. So 30 books in total, which is 10 plus 20. And the rest are science books. So it's 120 minus 30, which is 90 books science books. So if we prompt GPT-4 with this problem, it's actually able to output something which really mimics our human thinking process or the system 2 thinking process, in which you can see, even though I'm omitting some of the words in the response, you can see that it's actually following something really, really similar. This kind of stepwise computation. First compute the number of literature books, the number of total history and literature books, and eventually they did a subtraction to compute the number of science books. And eventually it is able to give us the correct answer. So if you are interested in trying this example is actually available here on bit.ly/GPT-4 system 2. This might not be very surprising that a powerful model like GPT-4 is able to solve this grade school math problem using system 2 thinking. But what about system 1 thinking? In order to mimic our system 1 thinking, we simply modified the prompt by adding this instruction, directly output the answer. And this will basically force GPT-4, given that it's pretty good at following instructions and following especially instructions about formats, this forces GPT-4 to directly give the answer. So it does give us kind of the answer in the desired format, which is the final answer. But unfortunately, this final answer is wrong. And again, this example is available here. This might be quite surprising because this is such a simple problem. And yet, it seems that GPT-4 or the language model we have cannot do this type of system 1 thinking. And there are actually more examples like this, which might seem even more obvious to a person. For example, if you ask GPT-4, which is closer to Ogden, Utah, the Empire State Building or the moon, you already give the answer, do not think step by step. And it's surprising that GPT-4 even fails at such a simple task. This is an example, by the way, discovered by my PhD advisor, Stuart Schubert. So the question that we have in this research is it possible for system 1 reasoning in language models? So people might say, oh, maybe this is not possible. Why do you think this should be possible? So the reason why we think it is possible for language models to perform system 1 reasoning is by looking at its internal architectures. So when we open the black box of a language model, actually in a language model, there are multiple layers, and even in producing a single token. And then a pretty obvious thought is that why can't you just use each layer to perform one step in the intermediate computation? For example, in this assuming kind of book example, why can't it use one of the layers to compute the number of literature books, and then the next layer to build up upon the previous layer's computation result to compute the total number of history and literature books, and then yet the next layer to compute the number of books that's left in the bookshelf. And this is, by the way, I'm only kind of like visualizing 4 layers, but actually a language model, a state-of-art language model like GPT-4 must have a lot more layers than this. So we don't know the exact statistics of GPT-4, but what we do know is the statistics of GPT-3. So even in a GPT-3 model, there are actually 96 layers. So here I'm trying to visualize the number of layers GPT-3 has, but doesn't even fit on the slide. So I'm just kind of like plotting it like this. And you can imagine, given that there are 96 layers, it might have the potential to solve a lot of to solve reasoning problems with a lot of steps by just kind of doing all the computations internally. And by the way, it not only has a lot of layers, it also has a huge hidden dimension, which is 12,000. So we believe it should be possible for language models to perform the type of system one reasoning. But then the question is, why can't they do this task really well, as shown in the previous two examples, the Asumi book example and also the Ogden Utah example. So one of the challenges is if you directly explain a model for system one reasoning, it's actually pretty hard to learn it without the intermediate supervision. So imagine if there's some intelligent Martians who arrive at the Earth and they have never seen what is a multiplication problem, and you just show them example inputs and outputs of the problem. So this is kind of the two inputs, and this is the output of multiplication, and just show them a bunch of examples and ask them to directly predict the output for a new input pair. And obviously, this might be really hard because without showing the intermediate steps, it's hard to figure out what is the internal computation that's required or the process that's required for transforming the inputs into the output. So one of our observations or one of our insights in this work is that actually chain result serves two purposes in training and generation. So one of the purposes is the chain result acts as a type of intermediate supervision, which makes learning the reasoning task easier. And another usage of chain result is it can also serve as a scratchpad, which makes solving the task at generation time easier. And these two aspects can actually be potentially separated from each other. And we can have viewing from this lens, we can revisit the existing system one and system two reasoning paradigms. For example, in normal chain result reasoning, which we call explicit chain result reasoning, we can see that during training time and also during generation time, we are both using the chain result. For example, during training time, we train the model on examples with the inputs and the intermediate computation steps before generating the output. So during training time, we are using the chain result steps. But at inference time, the model is also allowed to output these intermediate chain result steps and use them as a type of scratchpad, such that they can store the intermediate computation results before they compute the final output. And if we directly train the model for system one reasoning, which we also call it no chain result setting, then we are actually not using chain result both at training time and inference time. So for example, during training time, we train the model on examples where we do not show any intermediate steps. During inference time, we do not allow the model to use the intermediate steps as scratchpad. And obviously, this makes the task really hard and challenging for the model to learn even at training time. But in between, there's a middle ground, which we termed implicit chain result in this work, which for which we are referring to this during training time, we are allowed to use the chain result steps to make the training task easier. But at inference time, the model is not verbalizing the chain result steps. So during training time, with the supervision of the chain result steps, it is possible for the model to observe what is the process for transforming the input into the output. But at inference time, the model is not allowed to use these intermediate steps as a type of scratchpad. Instead, it needs to basically use its own internal hidden states to perform all the intermediate computation and directly give us the final answer. And we call this way of training and inference the implicit chain result paradigm. So how do we achieve implicit chain result? So as we mentioned in the really beginning, in the human brain, there is this internalization process, which internalizes the system 2 reasoning into system 1 reasoning through repeated practice. So we are we draw a parallel between this internalization process in the human brain and this algorithm for teaching the model to gradually internalize system 2 reasoning into system 1 reasoning. And the resulting algorithm is actually pretty simple. So we start a language model trained for system 2 reasoning, for which we train the model to produce the intermediate chain of thought steps before we produce the final answer. So conditional input, the model is trained to first produce the chain of thought steps, and then it will produce the final output. So we call this stage 0. At this stage, it is pure system 2 reasoning. So now at stage 1, after we have trained the model well on stage 0, we remove the first chain of thought token, and then we fine-tune the stage 0 model on this new format of training data, for which the model needs to directly output the second chain of thought token and onwards before producing the final output. But it is not allowed to produce the first chain of thought token. So the model needs to find a way to internalize this first intermediate step in its hidden state, such that it can directly start from the second chain of thought token. And we fine-tune the model until it's able to do well on this task. And then we go to the next step, where we remove yet one more chain of thought token before. So the model now needs to directly output from the third chain of thought token before producing the final output. And we keep repeating this process until eventually all the chain of thought tokens are removed. And then the model now is directly trained to output the final answer given the input. And at this stage, the model has achieved system 1 reasoning. So this is the final model at inference time is exactly the same as a no chain of thought model, but this process is basically providing some form of scaffolding for the model to learn the process of how to gradually internalize system 2 reasoning into system 1 reasoning. So this is our algorithm. Even though this algorithm is pretty simple, there are a few additional tricks which really make this training works. So one thing we noticed was after a stage transition, for example, after we have trained the model to do well on stage 1, and then we want to transition into stage 2. The first problem we notice is there's usually loss explosions. So all of a sudden, the loss blows up. And this is because a model trained well for stage 1 is starting the prediction. The model is trying to output from the second chain of thought token. But after we remove one more chain of thought token, all of a sudden we are training the loss such that the model needs to start from producing the third chain of thought token. And there's this sudden change of objective function makes the loss explode. So in order to solve this problem, instead of directly only removing 1 token, 2 tokens, 3 tokens in this training process, we add some stochasticity in the training process, such that we remove some random number of actual tokens with a really small probability. So this is just to make sure that we do not train the model to fully commit to the number of tokens being removed at this current stage, such that it's possible that in this transition process, where all of a sudden we want it to remove yet one more token, we don't want the loss to blow up. And a second issue is basically we are using an optimizer which maintains some gradient statistics, which is IDMW in our case. And because it's maintaining this second order gradient statistics, and our training is different from traditional training in which the training objective is changing during this training process. So the gradient statistics, when we when we have transition to the next stage are actually irrelevant because the loss function has already changed. So we reset the optimizer states after a stage transition. Yeah, it's a new optimization problem. So after we apply these two solutions, the training is stabilized.
I think we lost Yuntian for a second. Is everybody able to hear me? I just want to make sure that the meeting link is working. Okay. Let me bring Yuntian back. Give me a second. Yes. We will wait for about 1 minute or 2 minutes so he's able to come back, and we will reconvene in a second. Hey, Yuntian. I think we lost you there for a second. We can't hear you. Okay. Folks, we appreciate your patience with the technical difficulty. We shall be back in a bit. Did anybody have any questions? Oh, he's back again.
Oh, hey, sorry. I think there was some kind of problem with my internet. Where did you lose me?
Please, I think if you bring up your presentation.
Yeah, let me share my screen again. Yeah, I'm sure. Sorry for that. I'm not sure like why the internet is like this. Hopefully it's not because of the snow outside.
I think it's completely fine. We lost you if you go up. Actually, we were, yeah. Just one more up. Yes, I think ending that after this.
After this one?
Yes, and I think you were talking about solution 2. Anybody else, please feel free to correct me if you thought we were further up. No, I think yeah, I think optimizer reset part. Yeah.
Okay. I see. Yeah. So I will continue for continue at this point. I'm really sorry for the internet issue. So that's the second point is about using optimizers that maintain gradient statistics, such as the commonly used optimizers like ADAM or ADAM W. And for our work, we are using the ADAM W optimizer, which retains moving averages of first order derivatives and second order derivatives. So basically, as we transition into the next stage, when we are removing one more chain of token, the loss function has already kind of changed to a new, different loss function, and the gradient statistics become no longer relevant after a stage transition. So in order to solve this issue, we simply reset the optimizer states after a stage transition happens. And when we combine this solution 1 and solution 2, we can basically stabilize training, and we can go into our experiment section. So the main experiments we did were actually with multi-digit multiplication. And one reason we use multi-digit multiplication is it's actually pretty challenging for a model to solve if the model is not allowed to output the intermediate computations. And a second reason is because this is a setting in which we can easily control the level of difficulty for the model by controlling the number of digits. So in the main results presented in this paper, I will be presenting results conducted on 7-digit multiplications. So the inputs are two 7-digit numbers, and the model needs to output the product of these two 7-digit numbers without using any intermediate steps. And the model we are using here is actually just a small model, GPT-2 Small, with 12 layers and about 117 million parameters. For the internalization process, we remove one more chain of thought token every 1/8 of an epoch. So after the end of an epoch, we will have removed 8 more chain of thought tokens. And also, as I kind of mentioned in the part on stabilizing the training, we also randomly remove some number of extra tokens where the number of tokens to be removed is proportional to this probability distribution. So basically, this distribution is pretty like it only removes kind of like more than one extra token with less than 30% probability. So it's removing some number of extra tokens with a pretty small probability, just for the sake of stabilizing training. And we can take a look at the results. So the two main metrics that we are looking at here are, first, obviously, accuracy. We want the model to be able to correctly predict the final computation result. And the second metric that we are interested in is the speed. And here, instead of measuring the absolute speed, we measure speed relative to a no chain of thought setting. So under a no chain of thought setting, this speed will be 100%. But here you can see these two bars from here are the results of a traditional explicit chain of thought reasoning model in which it can actually get 100% accuracy for this 7-digit multiplication problem. But the speed you can see is about 10 to 20% that of a no chain of thought model, because of the fact that the model needs to output all the intermediate computation results before outputting the final answer. So no chain of thought, obviously, you will get 100% in terms of speed, because we are comparing speed relative to the speed of a no chain of thought setting. But unfortunately, if you look at the bar at the accuracy part, you cannot even see the bar, because no chain of thought model is only able to get a 0% accuracy on this task. So if we directly train a model to do 7-digit multiplication, we just cannot do that. As I mentioned in the beginning, without showing the model the process of how to transforming the inputs into the outputs, it is very hard for the model to figure out the rule for multi-digit multiplication, just from example demonstrations. But if we use the internalization method mentioned before, you can see that it's kind of getting 100% accuracy, and also the speed is the same as no chain of thought. And by the way, this is not surprising at all, because after the end of all the after we remove all the chain of thought tokens, an implicit chain of thought model is actually exactly the same as a no chain of thought model. So the speed up should just be 100%. And I also mentioned these two techniques for stabilizing training. And here I'm basically like showing that these techniques are at least necessary under our current experiment setting. Here, the two curves I'm showing here are the training dynamics, where on the x-axis I'm showing the number of stages. So just to recall that at the end of each stage, we will remove one more chain of thought token. The y-axis is the accuracy. And here you can see that even for the implicit chain of thought model, sometimes the accuracy drops to 0. But this doesn't mean that the model is doing something completely random. It's just that the accuracy metric considers only a fully correct result as correct. And even if there's like a 1 out of 14 digits kind of being wrong, we will count that as a 0. But anyway, the green curve here is our method. And if we do not use this kind of random number of extra tokens to remove during training, you can see that it cannot learn this task. And similarly, we also see that optimizer reset is also kind of crucial under the current setting. And another interesting suggestion one of my landmates gave me is to consider why do we like internalize it from left to right? What if we internalize from right to left? So we term this setting as reset removal. But interestingly, removing from the right-hand side doesn't seem to enable the model to internalize the reasoning. And also, one hyperparameter we have in this training process is the number of tokens we remove, or how quickly we transition into the next stage. So you can see there's a trade-off here. The more quickly we transition into the next stage, the shorter it will take for us to internalize all the tokens. But the problem is the model might not have the opportunity to learn the task at the current stage yet. So in our current experiments, we were already kind of through experimentation, we are already using the kind of most aggressive removal schedule for which the model is still able to learn the task, which is removing 8 tokens at 1 epoch. But here the red curve is showing that if we want to remove, say, 16 tokens per epoch, the model will fail training. And if we remove, say, like even fewer tokens per epoch, then the training curve I would expect the training curve to be more smooth, but at the cost of longer training time, because we need more stages. Sorry, not more stages, more epochs for the model to have internalized all the channel sub tokens. So when we were doing the experiments, we were mainly focusing on like 5x5 multiplication, 7x7 multiplication, and up to 9x9 digit multiplication. And actually, the reason is because when we started the experiments, so we had an earlier work also on implicit channel sort, but in our earlier work, we were only able to solve something like 5 digit multiplication. So we were not that ambitious when we were kind of experimenting with this method. But later, we found that actually this approach can be scaled up kind of even further. So the large experiment we have tested so far is on 20 digit multiplication. And we just trained a single model to do up to 20 digit multiplication. And by the way, the model backbone architecture is still GPT-2 Small. It's 12 layers. And we found that you can get kind of pretty good accuracy even under this setting. And this is this is the demo that I think I mentioned in the abstract of my talk. And this implicit channel sort prediction is our model's performance. You can see that it's able to directly output the final answer without any intermediate steps. Whereas this blinking thing kind of below is explicit channel sort, in which it will also eventually get the final result correct, but it needs kind of a long generation process for the intermediate channel sort tokens. And this is the quantitative result of how the model is doing when we look at the accuracy per the number of digits in the 2 operands. And we can see that it's actually doing pretty well. Even up to 20 digit by 20 digit multiplication, the model is able to get an accuracy of 99.5%. But if we look at the speed up on the red panel, we can see that at 20 digit multiplication, the speed is 26 times the speed of the explicit channel sort. But you might wonder, for example, just like we have this 99.5% accuracy. So what's that kind of 0.5% for which the model got it wrong? So it's interesting that the model is actually pretty bad at computing multiplications with a lot of with repeated digits. This is actually an observation made by my colleague, my former colleague at AI2, who also works with my postdoc advisor, Professor Yuntian. So Hyun Kim found that when the numbers contain a repeated digits like 4, the model tends to get it wrong. And this is something that we are still looking into. We don't have a kind of hypothesis of why this is the case yet. And in addition to multiplication problems, given that this method is pretty general, as long as the model has, as long as the problem has this kind of structural input and result and output, we can apply this method. So we also conducted experiments on grade school math problems. So it's kind of the same kind of, it's the same type of problems as we saw earlier in one of the examples in the number of books example. And again, we can see that this implicit small method is able to get an accuracy, but this time it's not able to match the accuracy of explicit small. It's getting an accuracy better than no chain result, but is underperforming explicit chain result. But still, by fine-tuning a mutual 7B model, we can actually achieve no chain result reasoning model, which is able to get 50% accuracy in answering questions in the GSM 8K dataset, which is even better than the performance of directly prompting GPT-4 to do the same task. And one of the concerns that I initially had after we trained the model was whether the model learned the algorithm for doing the computation rather than just doing some simple template matching. So in order to solve this, so first of all, this model is actually able to kind of solve the problem that we have seen earlier directly, so the assuming kind of bookshelf example. So it's able to get the final answer correct, which is great. But in order to try to test whether the model actually learned the algorithm or not, we try to change the numbers in the original problem. So instead of 10, now let's try to change the number of history books to be 20. And we can see that the output prediction also changes correspondingly and is still correct. So because there are 20 books on history, plus 90 books on literature, which is 40 books on literature. So our 60 books on history and literature. So 60 books left. So it seems that it's able to kind of adapt to the numbers, or it learned, actually, it seemed to learn the algorithm which transforms the input into the output. And if it changes to 30, and again, this is correct. If instead of twice that many books, we change that into 3 times that many books, and still we got it correct. This time it will be 0 because 30 books on history, 3 times 30 is 90, so 120 books in total. So the number of books left is 0. But it's still not like doing everything correctly. For example, if we simply change the final question to be how many history books does the assuming have, where the number of history books is already given in the beginning, it's still trying to do this kind of computation instead of just directly outputting the number of history books, which is 10. So up to this point, I have presented, I think, most of the technical details of how to train a model using this method for kind of internalizing system 2 reasoning into system 1 reasoning. But the one question that we got asked a lot was, how does the model, especially the internalized model, solve the multiplication problem? So especially if you think about the fact that we show that a model with 12 layers is able to solve 20-digit multiplication problems. And it's kind of pretty impressive. And it's interesting question of how the model achieved this. So in order to test this, we try to probe a model after the internalization process. So here, we are using a kind of a simple example of 3-digit multiplication in which the input contains 3 digits times another 3 digits, and the output will be kind of the product of these 2 numbers. So the question now we have is the model internally replicating the channel sort steps? So because of the internalization process, one natural hypothesis is, or maybe the model is just kind of internalizing the same channel sort kind of steps in the channel sort, but it just somehow found a way to compress these channel sort steps into its internal hidden states. So in order to test this, we try to probe the model hidden states at each position to see if it can successfully probe the channel sort tokens at each position. And by the way, this is a simplification of the actual model hidden states, because obviously a model has multiple layers of hidden states, but here we are kind of aggregating the results per layer. So if something can be probed or detected at any layer, we will consider it to be kind of probed at this position. We made this simplification just to make this kind of visualization less cluttered. So here is the channel sort that we showed to the model in the training data to solve this multi-digit multiplication problem. And you can see that this channel sort actually contains two types of intermediate results. So this P1, P2, and P3, we call this the partial products. So for example, P1 is actually the first digit in the second number times the first number, and P2 is the second digit in the second number times the first number, and P3 is similarly the third digit of the second number times the first number. And so these are the partial products. It's like a one digit by n digit, one by n multiplication problem. And there's also this kind of partial sums, which is kind of accumulating the summations of the partial products we have at this point. And then we try to probe wider. So just to recall that in the algorithm for this internalization process, we were gradually removing kind of these tokens in the channel sort, and then the model needs to basically internalize these tokens somehow in its hidden states. So we try to probe the model's hidden states to see where we can identify these channel sort tokens. And this is the final result. So interestingly, we can see that the most high-level observation that we can make is all of the partial products can be probed in the final internalized model hidden states. For example, this P1, P2, and P3, you can see that each digit of these numbers, they can be successfully probed at some position in the model. But surprisingly, the partial product, especially the middle digits, it cannot be probed at the model. So this means that the model is actually trying to at least the model is replicating the partial products internally, but not all the partial product, not all the other partial sums. And here we are only showing an example of 3-digit multiplication. We also tested this on 4-digit multiplication and found the same conclusion. So this seems to be pretty consistent. And the second finding, if we look carefully at which position these partial products are detectable, you can see that actually they are happening at the earliest possible position. For example, here you might notice that all of these P1 digits, they link to kind of the hidden state above B1. But B1 is actually the earliest possible position for the model to capture the partial product P1. Because P1 depends on the first number, A1, A2, and A3, and also the first digit in the second number, B1. So this is actually the earliest possible position, and the model is in fact just doing this at the earliest possible position. And similarly, you can see that B2 is also the earliest possible position where P2 can be captured. And similarly, the same holds for B3. So it's interesting that the model is actually kind of successfully replicating the partial products, but not the partial sums, and also the partial products are captured at the earliest possible position. These are our main observations. And we have a hypothesis of why this is the case. So our hypothesis is the model is modeling, the internalized model is modeling all the partial products, but not all the partial sum, probably because it's actually eventually using a different algorithm to directly sum up all the partial products together, which might be the reason why a 12-layer model can do 20G multiplication. For example, if you imagine the model is actually following the exact way that we are kind of providing the model how to solve a 20-digit multiplication problem, if it's gradually accumulating the partial sums, then for a 20-digit multiplication problem, the model needs to basically accumulate a partial sum of a sequence of 19 numbers. And this might be hard to do in a 12-layer model because these partial sums, they have a linear dependency on the previous partial sums. But instead, maybe the model is directly using some other way to sum up all these partial products. But this is kind of our ongoing research right now. Yeah, but in conclusion, in this work of ours, our main observation is that the chain of thought in a model trained for reasoning acts as two roles. First of all, it provides supervision for the process of transforming the inputs into the output to make learning easier. And secondly, this chain of thought tokens also act as a scratch pad during inference time to make solving the task easier. But a key observation we make here is that there's a middle ground in which maybe instead of using chain of thought for both training and inference, maybe we can use chain of thought only for training, and for inference, the model can rely on its internal hidden states as a scratch pad instead of this human-like chain of thought tokens to kind of think about the problem. And one of the intuition or motivation behind this is that for the state-of-art models we have today, there are actually a lot of layers, and the hidden states are pretty expressive already. And given the large number of layers and the large sizes of hidden states, even without any explicit chain of thought steps, the internal states might already be sufficient to solve a lot of challenging reasoning problems. And our algorithm proposed here, which is step-by-step internalization, gradually internalizes system 2 reasoning into system 1 reasoning. I think this is a pretty kind of intuitive method and also pretty simple. Yeah, I hope that there will be more follow-ups on this. Yeah, that's all of my talk, and I'm happy to take questions.
Thank you so much for your time today, Yuntian. Folks, please feel free to ask any questions that you may have. It's a very interesting topic. So, Yuntian, is it okay if you still just give the presentation?
Oh, sure.
Keep it on. We might have some questions. Okay, if no one's going to ask a question, I think I'll ask a question then. Yuntian, this is something as you were going through the presentation I thought about, and this is coming from a more of a, oh, actually Jay has a question. How about we give Jay an opportunity to ask? Here you go. Jay, please go ahead.
Yep. Thanks for the presentation. So there was also a recent data set which was released, I think GSM symbolic. So I was just wondering if you have tested your approach on that data set, and whether maybe when you move away from, let's say, numbers to maybe more abstract variables, like how does the approach fare, or like do you think that would work, or like what's your thought on that?
Oh, that's actually a really interesting question. So first of all, thank you for the question. I think this is a great question because GSM symbolic is actually one data that we are working with right now. So basically now we are trying to kind of develop a method to solve GSM symbolic by extending this approach by basically trying to ask the model to output the program as an intermediate step for solving such questions. But this is still ongoing work. But I think it's a great question. Basically, one of the challenges that we noticed about this GSM symbolic data set is that when we were trying to use the program to solve this task, one challenge we noticed was basically it's harder for the model to try to figure out how to predict the result of executing the program to get the correct answer. Let me see if I can actually find. Yeah, so this is kind of an ongoing work that a former lab mate of mine, also such a student, and I are working on. So basically, like we have a kind of delectable version of the question, in which instead of the kind of variables, we have this kind of instead of the numbers, we have these variables, and then the output is a function of like a kind of how the output should be depending on the kind of the variable assignments. And one challenge we are having right now is given the variable assignment and also the function, how to directly answer without a kind of a Python program interpreter. This itself seems to be pretty challenging because we notice that the model is having kind of a hard time at predicting the final answer correctly based on the function and the variable assignments. But this is still ongoing work, so maybe I shouldn't kind of waste too much time on this. But thanks for the question.
Yeah, thanks for your comments.
Does anybody else have a question? Okay, I'm going to ask the question that I had. I think I was thinking from a very problem-specific or a domain-specific standpoint, where let's say we had 100 trillion parameter transformer, and if we were to do like an arbitrarily large multiplication, which is going beyond 20, as you showed 20 digits, I believe there was a conjecture that I was proving that if there exists an integer a and b such that the transformer gets the answer, possibly a times b wrong, there's a huge possibility that it would always get it wrong. Do you believe with this type of reasoning, it might actually get to a point where it is 100% accurate?
I can repeat your question. Like what do you think will be wrong?
So multiplication in itself, right now we are doing it for 20 digits and 20 digits, right? Let's say we go up to 40 by 40, or we go up to 1600 by 1600. We keep on increasing the number of, and let's say we're even taking the context window to be arbitrarily long. How do you believe this would behave as we go? Because I know that Yuntian, I think I forget the name of the person, but he found that with the repeated digits, there were some errors that were coming about, right? That was the case that you found. Was there any experiments that you did where you just increased the number of digits altogether, and you saw any patterns emerge?
Oh, I see your point. So when we increase the number of digits, yeah, I think obviously, I think I see your question now. I obviously you will kind of get it wrong at a certain point.
Okay.
We haven't kind of increased it to that scale yet. Because like training this is actually pretty expensive, especially we scale this to more number of digits. For example, on 20 digit by 20 digit multiplication, actually the channel size is over 1,000 tokens long. Because the channel size is not only like 20 by 20 times 20, it's actually containing both the partial sums and the partial products. So it's more like 20 squared times 2, something like that. And when we scale up the number of digits, the training process becomes pretty long. So to be honest, I'm quite surprised that this method works on 20 by 20 multiplication for 12-layer model. And I'm actually not sure what's the limit of a 12-layer model in terms of the number of digits that it can solve. But I believe there must be an upper bound somewhere. Like you mentioned, like it definitely cannot solve, let's say, 100 by 20, 100 digit multiplication.
Just a follow up to that, do you believe, so when you say 12 layers, that is like 12 transformer blocks?
Yes, 12.
And even if we were to, let's say, create the positional encoding to be like infinite size, do you think that have you done any experiments on that front where you're changing those elements and trying to see if it retains the accuracy?
No, I don't think we will retain the accuracy, and it's not exactly the same kind of experiments as you mentioned, but we found that it's actually really hard for the model to generalize to a combination that it has never seen. So we did do an experiment for which, for example, we trained on up to 20 digit by 20 digit multiplication, but we leave out, let's say, all the multiplications involving a number of 5 digits. So we will kind of cross out kind of in the training data any kind of combinations involving like a 5 digit, and then we try to test it on something kind of on five digit number times some other number of digits within 20, and we found that the model is actually unable to learn this. But I feel that this is a separate problem. It's a generalization problem or interpolation problem. I feel that this is a kind of a pretty general problem of transformers or our current learning paradigm today, that it's really hard for the model to generalize to anything it has never seen during training time. So I say, like, the experiments that we were running are actually already simpler than the experiments that you are proposing, which is like extrapolation to something of a higher number of digits. You are doing something like interpolation. We just kind of try to kind of leave out a certain combination, certain type of combination during training, and we found that it's even hard for interpolation, not to mention like trying to extrapolate to something beyond what the model has seen during training.
Thank you for answering, and thank you for sharing your insights. I think there's someone named CS20B 1018S Manoj. That person has a question. What are the limitations of the current approach to implicit COT, and what are the potential future directions for improvement?
Yeah, that's actually a good question. I say, to me, one of the limitations that I've been thinking a lot is kind of the problem setup. So right now, for example, if you look at the accuracy numbers on, let's say, grade school math problems, if you look at the accuracy, actually implicit channel sort still underperforms explicit channel sort. So explicit channel sort accuracies are represented using the blue bars here, and implicit channel sort numbers are represented using the green box here. And you can see that there's still kind of like this kind of lagging behind behavior. And this might not be surprising because there's no free lunch. You can see that in the algorithm for internalizing channel sort in implicit channel sort, we are actually using the same type of supervision as explicit channel sort. So it's not surprising that there's no way this can outperform explicit channel sort, because essentially we are starting from explicit channel sort, and then we are trying to internalize the reasoning steps. So basically, one problem that we have been thinking a lot is how can we leverage this? Oh no, did I lose my internet again?
No, it's working. I can hear you.
Okay, great. So one thing we have been thinking a lot is how do we leverage the implicit channel sort paradigm to make it possibly kind of outperforming in terms of accuracy explicit channel sort. For example, one thing we have been thinking is, or maybe one benefit of implicit channel sort is it can actually adapt to different formats of channel sort. For example, in channel sort, some people might be using kind of like natural language channel sort, and there's kind of like works using a program as the channel sort, or also known as program of sorts. And maybe one of the benefits of implicit channel sort is, like after we have internalized everything, like we can probably leverage data of different formats, and maybe there's opportunity for outperforming the accuracy of explicit channel sort kind of along those directions. So we are basically like looking for problem setups for which implicit channel sort will kind of be potentially kind of like outperforming explicit channel sort. And another interesting thing that we noticed, especially when we kind of like talk to others, is we also noticed that actually for a lot of problems, single thought itself do not appear kind of useful. So, for example, we got a lot of suggestions of applying this to, let's say, common sense reasoning problems. But the one interesting thing we noticed was in common sense reasoning problems, actually, in some of the data sets that we tested, single thought itself is not helpful. So common sense reasoning is like sometimes like it is like you can read out the chain thought, but what we found was in a lot of problems, if we just train the model without the chain thought, it's actually outperforming the model with chain thought, or maybe there's like not kind of too much performance difference between with chain thought and without chain thought. In those cases, it's definitely not a good problem setup for implicit chain thought. Yeah, so basically, I think the short answer is I think we are looking for problem setups for which this might be kind of a more kind of practical method.
Thank you for sharing. Folks, do we have any other questions? Else, we're going to jump on to our research journey discussion and questions that we had for Yuntian. So any other questions? One last question. Okay, Jay Gala, please go ahead, Jay.
Yeah. So one thing you mentioned right now, let's say maybe chain of thought also might be in different forms, right? One is maybe like the standard string, and the other might be in the maybe functional form, like let's say as a function or something, right? So also do you think like that maybe it might be possible to, like, since humans also operate at different level of abstraction, right? Where they, depending on the problem and the complexity, they might choose like one form or the other, right? So how do you see like this sort of fitting in, like when we want to try internalizing chain of thought reasoning, or at least like also deciding, okay, what sort of let's say form I should use, or like how do you, maybe any comments that you have?
I see. Yeah, that's a good question. Yeah, we will be thinking something along those lines, but it's probably like still probably from a different angle. So actually, one of the future directions that we are really excited about, and I think I'm trying to allude to this point, is to how is that possible to do this in a progressive fashion by kind of gradually kind of composing these internalized skills at different levels. So, for example, one thing that that we've been interested in the beginning is, can we do something like predicting the output of executing some function, and then in this process, we notice that it's impossible to do that for functions, because in the functions there are a lot of arithmetic calculations that the model cannot kind of perform successfully. And then we realize that, in order to kind of solve kind of this kind of function simulation problem, solving arithmetic problems like multiplication is basically a necessary condition. So eventually we kind of like did experiments on multiplication. But then we were thinking, after this, a natural extension of this method might be we consider this at different levels. So for example, after the model is able to do all the arithmetic calculations, then maybe we can kind of go one step up into like kind of trying to learn to predict function execution results. Because in predicting function execution results, the arithmetic operations, they are kind of some basic operations. Let's say if in your function, you have a function like if A times B greater than C, then something happens. And in order to know which branch you should go to, you should at least be able to calculate what is the product of A and B, right? And we were thinking, maybe this internalization method should be applied in this kind of progressive fashion. It's like a person going through kind of like pre-K kind of grade school, like middle school, high school, until university. It's like maybe we should kind of design a hierarchy of skills, a hierarchy of reasoning skills, and we gradually kind of progressively kind of impose these skills such that eventually we are building upon the basic skills that the model has learned before to solve something that's more complicated.
I see. Thanks for your sense.
Thanks for the question.
I also posted investigating the limitations of transformers with simple arithmetic tasks and a couple of other algorithms that are used for like Karatsuba algorithm or certain primality tests, which are around arithmetics. It's interesting to see how these can connect with what we learned today. So thank you so much for sharing, Yuntian. But now we have some questions for you around your research journey. This community would love to learn a lot more. So one question we had was, what led you to focus on NLP specifically in your research? If you can talk about that a little bit.
Oh, sure. It's actually, I say, like, it's actually pretty random. I did my undergrad at Tsinghua University in China, and when I was a junior student, one of my friends went to a talk about artificial intelligence, but unfortunately, I didn't go to the talk myself. And he went to the talk, and then he told me something he learned from the talk, which turned out to be not a correct understanding of the talk. But back then, I was like, oh, I was really impressed about this concept of artificial intelligence. But back then, I had no idea of what is artificial intelligence research. So I decided to apply to some graduate programs to learn about AI back then. And I learned, and back then I really didn't know what is kind of, what are the available research directions, what should be my kind of focus, that kind of thing. So I just kind of wrote a kind of statement of purpose saying that I'm interested in AI and I wanted to kind of study in such a program. And I submitted my applications to a bunch of graduate programs. And by the way, like from today's standard, if in today, if someone does such a statement of purpose, they probably wouldn't get any offers. But back then it was pretty early in AI. So I thought I say maybe back then it was easier. So eventually I got admitted into the master program at LTI at CMU.
Oh, wow.
And there I started to learn what is AI, and I started to learn about like neural networks. And when I started learning neural networks, I was very disappointed. Because like back then, in my imagination, I was thinking, oh, AI was something, by the way, this is what my friend told me. You know, it's something like, AI was something like, oh, you cut a kind of the brain of a mouse into slices, and then you kind of try to teach it to do something, like navigating the maze or something. And then when I started learning at LTI, I realized that it's just kind of a bunch of metric multiplications, some nonlinearities. And I was so disappointed. I was like, how can this lead to anything that's remotely close to intelligence? But yeah, so if it's always that, maybe I would just kind of graduate and never pursue a PhD. But then in 2016, during lunch, I had a conversation with a friend of mine, and she told me that there's something called sequence-to-sequence learning, in which they have like a kind of a model which reads an input sentence and compress that into a vector, and then a decoder model will take that vector and produce an output sequence of words, and they use this for machine translation. And I was like, oh, but this doesn't sound reasonable to me. How can you compress information kind of in a variable length sentence into a fixed size vector and then apply the decoder to kind of decode it back into some sentence? There must be some kind of information loss in this process. And then this friend of mine told me that there's something called attention, which exactly solves this problem. So then I read the attention paper, and I was like, wow, this is such a kind of great idea. And I really wanted to kind of work on this. And then I tried to basically like search for kind of professors' names. And then I saw that my kind of later PhD advisor, Sakar Raj, he had a paper on neural affective summarization, which is one of the first works on applying neural sequence-to-sequence learning with attention to summarization or to text generation in general. So I decided to kind of like to join his lab to kind of learn more about this, and this became kind of eventually my kind of PhD direction. So I say it's pretty random. It started from like the misinformation from my college friend, and then during master it was, yeah. By the way, the neural sequence-to-sequence with attention paper was actually published in 2014. but I only learned about it in 2016.
Even
yeah,
though
but
paper came in like 2017 or something, right?
oh yes, that's right. That's right. Yes. So I say like it's a bunch of coincidences.
Thank you for answering that. And I think one question that oh, actually, did you take classes with Graham Neubig at LTI?
Oh, unfortunately not.
Okay.
Yeah.
Um,
Yeah, because I think I took classes with Chris Dyer, but eventually he left for DeepMind.
oh wow. Okay. Another question we had for you is almost all of your past research has, as I was going through it, it has really interactive demos, and they're awesome. They really help understand the material a lot better. So what has been the inspiration behind this? And did this idea come from somewhere, or were you like, as you saw more people who were reading your research, it became a lot more easier for them? What was the inspiration behind that?
Yeah, I say like rather than kind of like viewing this from a point of view of like maximizing kind of like how people view my research, this is actually because of the fact that I think my PhD advisor Sacha Raj, I think he greatly kind of shaped my research direction to say the least. Because as I mentioned, like I knew nothing about research when I started kind of doing my kind of master program. Um, and Sacha, he was really into kind of programming and kind of coding up demos. So my first author paper is about kind of converting an image of a math formula into the latex of that math formula. And Sacha wrote a kind of a visualization code for me using D3.js. And I say like it's mainly kind of like a kind of shaped by theme. So Sacha is like my role model, like I mentioned. Like I wasn't kind of familiar with research. Basically, I learned everything from him. I try to kind of replicate the way he's doing work. He's doing research, and he's really into demos. And I say like this is kind of a big kind of factor of why I kind of became like this way. And in this process, I feel that I really enjoy doing this. I feel that one benefit of building a demo is basically like you make sure that people can replicate your work. One thing I found really I felt really frustrated sometimes is I read a paper and I cannot find the code of that paper.
Right.
Or sometimes like I read a paper, I found the code, and then I spent a few months and I couldn't replicate the numbers in the paper. I feel that that's even more kind of a waste of time. So I think like one nice thing about building a demo is basically like by releasing the model checkpoints, by releasing the logs, I'm making sure that like my works are reproducible by others.
I think that's an awesome inspiration. I think research reproducibility, especially in AI, is so important. And I think that the demos are just amazing. They're fascinating. I think they generate a lot of interest too. So I think the third question that we had was around if you can share any pivotal moment or a project that significantly shaped your research direction. Was it the one that you already talked about?
Yes, I say so. Like I mentioned, like before I started, I basically had like no kind of like a kind of real kind of research training. And in my the first author paper, this kind of like image to latex kind of conversion stuff. Basically, I learned. Yeah, I can't even like pinpoint exactly what I learned, because I learned so much. Like basically, Sasha helped me kind of write the entire paper. Like I just kind of basically like filled in the numbers in the table, and in this process, like I mentioned, like it feels like training a language model. It's like a teacher training. I mean, teacher processing, in which I observed how he was kind of doing things. I observed like he was kind of building visualization for kind of like a kind of for this entire project, and this I think kind of greatly shapes kind of how I do kind of this type of research going forward. I feel that one of the most precious experiences of doing a PhD is to be able to basically like work with these great people and try to like mimic how they are doing things. I feel like it's very similar to like in the like Middle Ages, like for example, stone masons, they by kind of doing some kind of apprenticeship, they kind of try to kind of learn some skill of trade. And here I think there's like a striking similarities here.
Thanks for sharing that. We appreciate that. Another question that we had was, as you've worked a bit in the industry too, it seems like you've had some connections there. What's the one thing that you were strongly opinionated about in terms of pursuing research altogether? And what have you changed your mind about after seeing some experience in the industry too? How has it shaped your journey a bit?
Oh, I say like the biggest lesson that I learned is just like we want to keep things simple. It's usually the case that if something is not simple enough, it usually doesn't work in practice. So for example, I can share like some stories I heard in industry. For example, I know someone who basically there was like you mentioned like in 2017 there was the transformer paper, and then there were a lot of follow-up works on basically like making this and that like minor tweaks to the transformer architecture. And then I heard a story in industry that someone basically like led a team to try all these proposed variants in these kind of papers. And obviously every paper must be claiming that their variant is better based on some empirical numbers. But this person is trying to kind of like replicate all these results, but under a much larger scale. And then what he finally found was under a large scale, like none of these variants actually perform like significantly different from the vanilla transformer architecture. So I say that the biggest lesson I learned is that you want to kind of keep things simple. If something is not simple enough, usually it wouldn't be practical. Like at a scale, you probably wouldn't kind of be doing that well. For example, one of my kind of own research lessons is I once wanted to kind of incorporate some linguistic features into a machine translation system. But what was interesting was throughout experiments, I found that the larger the training data set, the less it seemed to matter. And it was like I was like a really kind of a little bit kind of even like a depressed back then, because the research process is we started from smaller experiments, and then when we see it working, we gradually increase the scale. But in this process, I was more and more convinced that this is not something that we should pursue, because beyond a certain scale, this is not helpful at all. So eventually we just kind of gave up on that project. But I say like my kind of the biggest lesson I learned is like I value kind of simple changes that really make a difference, rather than like a fancy kind of system. For example, I remember at a point I was doing research in latent variable modeling in language, in deep learning before. And at a point, if you read kind of these machine learning papers, there were a bunch of people who could make really complicated graphical models. But the problem is just that maybe it's sufficient for publishing a paper, because they look kind of to be innovative in some way. But when you actually scale this up in the industry, first of all, it might be already kind of too complicated to incorporate into existing workflows. And secondly, at a scale, usually like these things do not kind of help.
Oh, thank you. And I think before we wrap up, one last question. What are your aspirations for the future impact of your research on AI and society in itself?
Yeah, I think that's a really great question. So last summer, I gave a talk at the NYU summer school, and where I was talking about, it was like a kind of intro to NLP, the kind of like tutorial class, and I was talking about basically the seminal works that shaped the NLP landscape today. And then there was someone from the audience who asked me a question. So Yuntian, what's your contribution to this graph? And I was like, oh, this is such a great question. So actually, after I kind of think about that for a while, there's a concept in interpretability research called Shapley value. Basically, how important a feature is. In order to test that, you kind of remove that feature and see how much that affects the performance of your final system. And to be honest, I have one of the biggest concerns or fears these times is it's just that I feel that even if I am removed from the kind of academic community, I honestly, I don't think there will be kind of much difference with me or without me. So from this point of view, my Shapley value might be pretty low. but I hope that like at least some of my works will be kind of useful like in the long term. And to me, I feel that it's really hard to predict. But at least I'm trying to make sure that other works I do at least excite me. I mean, like at least it will make me feel excited. And hopefully they will have a slight chance of eventually kind of affecting the mainstream research. But I say like my actual expectation is probably lower than that. It's just like at least I could feel kind of excited about my own research. And I feel that that might be kind of a necessary condition, or even probably make it more likely that my research will be useful for the kind of broad community.
Oh, wow. We really appreciate you being so candid. Thank you so much for sharing this. We really appreciate your time today. Does anybody else have any questions? Else we will wrap it up. We're at time now. I guess no.
Yes, thank you everyone for listening at Saturday. Really appreciate that. And feel free to kind of drop me an email if you have any further questions.
Thank you so much. And I think maybe I can share your email with them, or it's
Yeah,
already
sure.
on the website. Or
yes, I already public information, so feel free to share.
Cool. Thank you so much, Yuntian. We really appreciate your time today.
Thank you so much for inviting me.
Ciao. Bye-bye.